So we've seen linear factors and linear repeated factors. Now I want to look at quadratic factors. Really, what I mean by that is quadratic irreducible. So it's second degree, and you couldn't factor it down to first degree. So here we have an example. And again, remember, strategy-wise, partial fractions is going to be applied to situations where you have a rational expression, which is what we have, and that the denominator has factors. So we can do a little bit of factoring there, right? We can take a t out on the bottom. And we have t times t squared plus 1. So, and that's as far as that goes, right? T squared plus 1 doesn't factor any further. It's irreducible. And then we have that single linear factor outside. So we have a combination. One of our factors is linear non-repeated. We know how to deal with that. But this is new. Quadratic here, irreducible. So again, the only thing that's going to change is how we're going to set up that algebra. After that, we'll continue same as we always have. So let's rewrite this. In our setup here, we've got 3t squared plus t plus 4 over t times t squared plus 1. Now, we know how to deal with a linear one. That linear factor just gets a constant up top, and it's not repeated, so it's just there once. The quadratic, and here's the logic. This is linear, first degree, right? That's a constant, 0 degree. So that's 1 degree less. That's as high a degree as that could be without being an improper fraction. So the same idea applies here. This is t squared plus 1. So the idea is we want to write an expression that's as general as possible, but is still a proper fraction. Because if it was improper, you could divide and reduce it down. So that's second degree. I want a first degree expression up top. So a first degree expression of t would be some coefficient times t plus a constant. So quadratic irreducible factors will get a linear expression up top. Linears get a constant expression up top. Now we just continue in the fashion that we did in the past. Multiply both sides by this common denominator to clear our fractions. So over here, we're going to have a times t squared plus 1. And then bt plus c is times t. Now, shortcut-wise, you could plug in a t equals 0. That would get rid of all that, and you could solve for a. A would be 4. So you could do a little bit of shortcut. But now you see the problem with quadratic irreducibles is in their nature of being irreducible, they have no 0. There's nothing I can plug in for t that makes that 0. If I could, then I could factor it. So by definition, being irreducible means there's no number I can plug in there to make that 0. So the shortcut does not really work on anything involving quadratic irreducible. So you could do a mix. So we could find a right now. T equals 0 would give us a equals 4. But again, there's not a whole lot of unknowns in there. And I'm just going to do the whole thing by matching coefficients. 3t squared plus t plus 4. What do we have for t squareds over here? We're going to have at squared and bt squared. So we have a plus b t squared. What do we have for t's? Just this, right? C times t. So c is the coefficient on t. And we only have one constant, a times 1. So plus a. Now, match coefficients. Coefficient on t squared is 3. Over there, it's a plus b. So a plus b should be 3. Coefficient on t here, if you like, you could write a 1 in there. Coefficient on t is 1. Coefficient on t is c, so c is 1. So that's nice. We just know C automatically. And look at this. A we could have gotten by the shortcut, but it comes out quite nicely and easily here in the matching coefficients. So we also know A is 4 from that. So this is quite nice. 3 unknowns, but really 2 of them fall out right away. If A is 4, 4 plus B is 3, so B is -1. So we have all of our unknowns. So let's return to our problem here. Again, being careful to plug stuff in the right place. A was that constant on top of T. And then on top of T squared plus 1, we had BT plus C. So -1T plus 1. Or -T plus 1. Now, this one, we know that's natural log. This one, at this stage, no matter what had happened over here, we're going to have something times t plus a constant. Notice that no matter what those are, if we break that apart into 2 fractions, we have stuff, we'll always be able to integrate this. So the fact that that's quadratic does not mess things up. We've got -t over t squared plus 1, and we also have 1 over t squared plus 1. Now let's see what we have. Again, we know how to do that, natural log. This one, remember, that's the derivative of tan inverse. We know that one. All we really have is that middle one. But no matter what that coefficient on t had been, we could always just take it off. And you have t over t squared plus 1. Well, the derivative of t squared plus 1 is 2t. So u substitution works just fine there. And so what we would have after our u sub is a half natural log absolute value of t squared plus 1 plus tan inverse of t. So I was just saving a little writing here by not going into the details of the u sub. If you aren't seeing how you would go from there to there, just actually go through the details. U would be t squared plus 1, and you'd end up at natural log of t squared plus 1 times a half. All right, so what have we looked at? We've looked at linear repeated. Now we have quadratic irreducible. We also need to look at quadratic irreducibles that are repeated. So we'll look at that next time.